All right, so there are 3 coordinates atoms, 4 atoms. This is a 12-dimensional problem. All right, so if we wanted to write a harmonic oscillator for this function, a potential for this function to solve the Schrodinger equation and calculate wave functions, we're going to have wave functions that have 12 coordinates in them. Right? The wave function will be a function of every coordinate of every atom. Well, that's kind of annoying, right? Because that's a really hard thing to track. Now imagine if you go to benzene, right? You go to a bigger molecule, right? Benzene's got 12 atoms, right? 12 times 3 is 36. It has 36 coordinates to choose from. So the motion, the vibrational motion of this molecule, formaldehyde, the potential is 12-dimensional. Well, that's not very nice for us because, again, we discuss this molecule in 3 dimensions. We don't really interpret it as a 12-dimensional object. It's a 3-dimensional object. Right? But we have 12 degrees of freedom, so the potential will have 12 coordinates. So we've got to come up with some way to simplify that. And even worse, as we'll see, that these coordinates aren't necessarily independent from each other. Let me give you an example. Right? These coordinates are dependent on each other. For instance, imagine I took my formaldehyde molecule, okay, and I stretch a H bond. Right, so the molecule now looks like this. Something like that. Okay? And now I want to ask the question, how does the stiffness of the CO bond change between here and here? Because now I have a different structure for the molecule. Right? If you think about this molecule, if I just stretch the CO bond without stretching the H, if I stretch this, right, it has some force constant. We'll just say it has some force constant K. Right? And so it's stiff at some amount. But now what I do is I stretch the H and I ask the same question, how stiff is the carbon-oxygen bond? What's the vibrational frequency of that motion, CO stretch? Well, I've weakened this bond, for instance, in this carbon, right? So I've appreciably changed the electronic structure of the carbon, right? Which is going to inevitably change the environment or the chemistry or the stiffness of the CO bond. Right? I've gone from a molecule that's low energy equilibrium, and I've stretched one of the coordinates. Now I've changed the covalent behavior of this carbon, right? Because now that hydrogen is leaving, right? So you can kind of think of this as a homolytic cleavage where you have a little bit of a radical and a little bit of a radical there. You're starting to break that bond, right? And the covalency of carbon changes, right? As I start to homolytically cleave that CH bond. And so therefore, when I stretch my CO bond, that carbon has a different chemical environment now than it did before I stretched the CH bond, and therefore it's going to have a different force constant. Right? So if I move one set of coordinates, it's going to affect the physics of the other coordinates, right? Because as I stretch a bond a certain distance, it's going to affect the electronic structure, the electronic environment of the atom attached to it. Right? So that's even scarier. Right? The nice thing about the harmonic oscillator approximation, again, is that it's orthogonal. Right? That coordinate doesn't, well, there's only one coordinate in diatomic, but the idea is that if there were more, one motional on one coordinate doesn't affect the other one. We want it to be orthogonal, right? That's the whole point of quantum mechanics, is we want to represent these motions and these physics as orthogonal motions so that they don't interfere with each other. So we don't have to worry about these things, right? We want to think about how this molecule stretches the CO bond without affecting the covalency of the hydrogen of the carbon, and vice versa. Right? We want to have some way to think about vibrations without having to worry about which gets stretched first. Okay, so we have a 12-dimensional problem, and all these coordinates are not orthogonal to each other. They're coupled to each other. You move one, you affect the other one. Or rather, I should say that if you move one coordinate, you affect the potential energy of another coordinate. Potential energy changes, or K. The force constant changes. So we have to come up with some way to represent these vibrational motions of a polyatomic molecule so that we don't have to worry about these couplings, right? That we can represent the fundamental motions and vibrations of a molecule without having to basically worry about K changing, right? We have motions that are invariant, right? That they're kind of quantized motions of the entire molecule, collective motions of the molecule, that conserve these kinds of things and therefore have independent coordinates. Okay, so we can think of one vibration independent of another. And that's going to be our focus today, is how do we get to that point? Right? So what do we want? We want a set of independent motions, vibrational motions, that are uncoupled, which means they don't affect each other in the way I just described, and are represented by a harmonic oscillator. Okay, so we ultimately want to represent the vibrations of this molecule as a set of independent harmonic oscillators. Right? And there's going to be a selection of them depending on the molecule. And we're going to have to come up with some mathematical formalism, some way to take our complicated system, all these coupled coordinates, and convert it into something where the coordinates are uncoupled and collective, and they're each represented by a specific harmonic oscillator, in the sense that each motion has its own force constant. Right? All right, we'll see how that happens today. So let me try to set up the problem a little bit. So let me go ahead and draw my formaldehyde again. Nice big formaldehyde. All right, and let's assume each bond is at its equilibrium position. Okay? So you can think of an atom as a bunch of springs, or you can think of a molecule as a bunch of springs. Right? What those springs look like, we're not sure yet, but they're all at equilibrium, right? They're all sitting at the minimum of their potential. Molecule's just floating in space the way it wants to at ground energy, and it's not doing anything. Okay? Right, so we're at equilibrium, just like we were before, right? The R sub E. Right, so we have an R sub E for each of these bonds. You can say the CH bonds have an R sub E and the CO bond has an R sub E. Right, and so we can write the coordinates of each of those atoms at equilibrium. So let the coordinates at equilibrium for the nth atom be x in, let me do it like this instead. N sub 0, y n sub 0, z n sub 0. Okay, so the 0, again, n means it's the nth atom, and the 0 there just means that they're at equilibrium. You can call it E if you want. It doesn't matter. I'm just going to use 0. All right, so these are your equilibrium coordinates for each of your atoms. All right, so this, of course, would be, for instance, XH0. Well, this is H beta. I'll just write a B on top of it. YH beta 0, and ZH0 beta. Okay. All right, and we also need to know the mass of the atom, right? So let's say the mass of the atom, of course, is m sub h. We have a mass. I'll write it over here so it's a little clearer. All right, we have an m sub c, an m sub o, m sub h, and so on and so on. Right, they each have a mass. All right, and what we're going to do now is we're going to displace each coordinate separately. All right, we're going to jiggle the atoms individually a little bit, okay? So let's now displace the atoms. All right, so maybe I move this one this way, I move this one this way, and I move this one this way, for instance, right? So now I displace the atoms. Okay. And I want to displace them in such a way that the center of mass doesn't change, all right? And the COM, the center of mass, stays constant. All right, doesn't move. All right, so I'll draw the center of mass for the molecule. It's right here. All right, so what I'm going to do is I'm going to move the atoms in some combination. I can choose any combination you want, but I want to do it in such a way that the position of the center of mass doesn't change. Okay, so if I stretch the two hydrogen atoms down away from the center of mass, the oxygen has to go up, equal and opposite based on its mass, right? So if we stretch the bonds, then the oxygen also has to move symmetrically with the hydrogens to compensate for that. And so what we do is we define, in order to do this, to show this, we define what are called mass weighted coordinates okay, for displacement. Okay, and so we'll call the coordinates of displacement delta x sub I, or delta x sub n, which is the square root of the mass. Let me do it, yeah, I'll do it like that. The mass of the atom that's moving times the displacement coordinate, which is x sub n minus x sub n sub 0. Okay, so what I'm going to do is I'm going to jiggle these atoms in some direction. It doesn't matter which direction I do, but I'm going to do it in such a way that I define the coordinates to be mass weighted by the square root of m. All right, and the coordinate is going to be the displacement, right? That's how much it's moved away from equilibrium. Okay, so all the coordinates are basically scaled so that when they're not moving, they're at 0, some equilibrium position, and I'm moving them away a little bit like this. I'm stretching them or compressing them and moving them around. Of course, there's 3 n of these, right? Because there's 3 n coordinates. I'll write that here. There are 3 n of these. Okay, and what I'm going to do now is I'm going to think about how, remember, ultimately what we've got to think about is how does our potential energy change of our system? Remember, we're always going back to the Schrodinger equation. We know how the kinetic energy of these atoms are. They're just a function of the mass and the second derivative of the position. So that's easy enough to do. We can write that down. But we have to think about how the potential energy changes as we move one of these coordinates. But again, the potential energy surface is 12-dimensional. So we're going to have to be very careful about things and make sure that we count for everything, because we have 12 dimensions in the case of formaldehyde. All right, so let's remind ourselves really quickly how we did this for a diatomic. So now what we're going to do is consider what V of delta xn looks like. Okay? So we're going to approximate what the potential looks like at equilibrium, which is where there's no displacement, and we're going to calculate a function or some approximation for the function around that equilibrium point. All right, we're just going to move things a little bit away from equilibrium and see how the energy changes. All right, so for diatomics, V of delta xn looks like the potential at the minimum plus, remember, the linear part, right? We're just doing a Taylor approximation. So we calculate the slope of the curve at the equilibrium point and multiply it by a linear function in x. All right, let me change this to delta x, using delta x. And then we have, at the very least, a second derivative, a quadratic approximation. Delta x squared. Okay? So again, we're doing something very simple. We don't know what the potential looks like. But if we can calculate some derivatives, right, if we can measure these parts of the derivatives, the parts of the potential, the slopes around it, we can calculate an approximate function that looks, again, like a harmonic oscillator, right? It's something that's an x squared. And of course, this term goes away, just like it did in the Morse oscillator, because we're at minimum. Right, this goes to 0 because because equilibrium is at a minimum of energy. Okay, and we can always set this to 0 by letting V of xo just be set to 0, right? We can set the energy equal 0 to any point we want. Right, so we can always just scale the system so that the energy at the equilibrium is 0. We just define our energy scale that way. And the first derivative term goes away because we're at a minimum. Right? We're expanding around a minimum of an energy surface. And so all we are left with is this second derivative term. And of course, there's higher order terms as well. I'll just add that. All right, there's more terms. Okay, and again, this is why we do a harmonic oscillator approximation, is because if we don't know what the potential looks like for a diatomic, we know that for the first major part of the potential, when we vibrate a molecule away from equilibrium, is a quadratic part, 1/2 some number, which is k, x squared. Right? This is just a harmonic oscillator potential. Right? But it's important that we write this down explicitly, because this gives us a way to write a formula, as you'll see in a second, for as many dimensions as we want. All right? This is just one-dimensional, but now we have a 3n-dimensional problem. And the nice thing about this is this gives us a really, really nice way to calculate and write down a formula for approximation for what we think the function will look like in as many dimensions as we please. We'll kind of screw this over a little bit here. Okay, so now what we have is a potential. All right, so now let me just do this for a polyatomic case. Our potential now is now a function of delta x1, delta x2, all the way up to delta x3n, right? Because there's 3n coordinates for an n-atom molecule. Okay, and that's going to be equal to the potential evaluated where everything is set to 0. Right, this is the potential at equilibrium. Okay. And then we have the linear term, which we know goes to 0, but I'm going to write it anyway. But there are now the question is, of course, in the linear term, we have to take derivatives, right? Remember, let me go back one more time. And again, let's look at our linear term in our, which of course is 0 here, but let's just write it down. Right? The linear term takes the derivative of the potential with respect to the coordinate, right? The slope of the curve along that coordinate. There are 3 n coordinates. So in order to define a 3 n potential this way, we need 3 n slopes, 3 n derivatives, one for each one of the coordinates. So we have to add a sum here. The sum from I equals 0 to 3n of the derivative of the potential with respect to that coordinate, x sub I. Delta x sub I, sorry. And it's evaluated at the equilibrium point, which is x sub I, sorry, delta x evaluated at the minimum of the potential, which is delta x sub I equals 0. And this is multiplied by delta x sub I, right? That's our linear term. All right? This will go away, right? This goes to 0. Nothing's changed. We're still evaluating how the function changes as we move away from the minimum at the bottom of the potential level. So it's still so the potential, the slope of the potential at the minimum, no matter which way you go, is still 0. Still a minimum. So this term's going to go away, but it's important to note that, again, we have 3 n terms. We have to sum over all of them because there's 3 n derivatives. You have a term for each one. Now, what about the quadratic term, right? The first term that actually shows up. Right? So that term, let me just go back again. Sorry. Takes a second derivative of the potential with respect to the coordinate. But now we have coordinates that are coupled. Right? So we could take a second derivative with respect to the function. Right? We have 2 options for the second derivative. So let me write it like that. So right, we have, because the coordinates are coupled, 2 possible quadratic terms. Right? One is, let me do it in a different color. One is 1/2 times the derivative of the potential, second derivative of the potential, with respect to one of the coordinates. And this is, of course, delta xi, sorry. With delta xi evaluated at 0, times delta xi squared. Right, that's one term. That looks just like what we had before. And of course, there are 3 n of those, right? Because there's 3 n x sub I coordinates. Right? There's 3 n coordinates. So there's 3 n of these. But there's also cross terms. Right? There's also terms that look like this, where you take the derivative of the potential with respect to one coordinate, x sub I, and then you take the derivative of the potential with respect to another coordinate, x sub j. And again, we evaluate both of these at 0. And we get delta x sub I, delta x sub j here. Right? So these are what we call, you can call these the diagonal terms. I'll explain why in a second. And then we have these off-diagonal terms. These are just the terms we use for these. Right? Or cross terms. Another term we use is cross. Cross terms. Right? So, and the reason why we have both of these is because, so what is this telling me? Right? What is this second term telling me? What is this telling me? It's saying that if I stretch along one of the coordinates, that it may affect the potential along another coordinate. Right? So as the potential changes as I move x sub I, that may induce a change along x sub j. Right? So as I move along x sub I, the slope and the behavior of the potential along x sub j will change as a function of x sub I. Right? So the 2 functions are, the 2 coordinates are coupled, right? As I explained before. Right? So these terms might not be 0. Right? And this is where it becomes very tricky to deal with things, because this is exactly Right? This is where the coupling comes in. We're saying that this means that if this is non-zero, I'll just repeat it in words. If this is not equal to 0, then motion along delta x sub I affects motion along x sub j. Right? That's what I explained with the CHs and the oxygens and stuff for formaldehyde. All right, so these terms are a real problem for us. Right? We want to get rid of these terms, right? Because what we want are a set of coordinates where they just look like harmonic oscillators along one coordinate, right? We want this thing at the top, the diagonal terms. We want everything to look like this. Because how does this behave? Well, you can move along any coordinate you want, any of the x sub i's, and it doesn't affect the other ones, right? There's no dependence on x sub j. All right, so we want these terms to go away, and we want to have everything, we want to pick a set of coordinates, rather, a set of coordinates x sub I and x sub j, where these terms are all 0 and these are non-zero. All right, so that means that we can move along these special coordinates, and it doesn't affect the other ones. Right? They all move independently of each other. And let me just write that down. Right, so if these are equal to 0, coordinates are independent and uncoupled. Okay. All right, so what we want, our goal is to choose a set of coordinates for our system where all the cross terms go away. How we do that, we're not sure yet. All right, but I'm going to give you a couple of, and in fact, the way that the way that a computer does this is very different than the way that a spectroscopist does it. But I'm going to give you the computer answer because it's actually quite interesting how it does it. It's a very simple idea. I think it's much more conceptually easy, though it's not as chemically obvious, the computer method of solving this problem. Not as chemically meaningful, but in terms of conceptually, I think it's pretty straightforward. Right, so what does this look like, right? So this is what we want, right? We want the cross terms to go away. Right, this is what we want. And the question is what do these coordinates look like, right? How do we choose how to move atoms in such a way that we can move them independently without having to worry about these coupled motions? All right, well, these coordinates are going to look, right, so these special coordinates, let me kind of put it over here real quick. These special coordinates will be what are called collective coordinates of the molecule. That are, and this is the key word, or key phrase, linear combinations of the atomic displacements. Let me tell you what I mean by that. All right, so these coordinates, I'm going to reintroduce this term, but I'm going to tell you what they're called. All right, I won't define it just yet, but I just want to use this vocabulary now. These special coordinates are called normal modes. I'll write that here. All right, I'll redefine this in a little bit, but just to have this term available for us, right? These special coordinates that I'm talking about where we can independently move the atoms collectively and it doesn't affect the other collective motions of the atom, these independent vibrations, are called normal modes. Right? In a normal mode, I will typically write in this class, whenever it comes up, as Q sub I. Right? That's the ith normal mode, if you will, Q. Okay? And Q sub I will be a combination of all the displacements of different kinds. Right? So it could be C1 delta x1 plus C2 delta x2 plus C3 delta x3 all the way up to C3n delta x3n, where the C sub I constants are weights. Right? They tell you how much each of the atoms move. Right? And the sum of the coefficients squared they're normalized, equal to 1. Okay, so there might be, for instance, in formaldehyde, coordinates where the hydrogens move a lot, right? That would have large coefficients on the hydrogens, C1 and C2, for instance, but the oxygen doesn't move very much. Okay, but they're all the atoms will theoretically have non-zero displacement in these normal modes. They're all moving collectively in some way. Right? So they're just linear combinations, right? Linear combinations of our individual motions. Again, we've seen this kind of concept before, very much in a much smaller way, when we talked about color and flavor. And the idea is that an electron with color is not white or black. It's a linear combination of white and black, depending on how you define and what state the system is in, the atom is in, the color of the system. But it can be in any combination of white and black. And here we have the same idea. We have a coordinate, something we can measure, like color, and it's a linear combination of systems of states that are represented by a basis of individual atom motions, right? Just like how color is represented in a basis of white and black. Here we just have 3n of those choices instead of 2. Right? It's the same concept. It's a linear combination of different motions. Right? So we have this nice math. All right, so let's put it all together. Okay, so once we apply, that the potential at the 0 point, which is at equilibrium, is 0, right? We're going to set the bottom of the potential to be energy 0, so we just get rid of that term. And we know that the derivatives of the potential with respect to each of the displacements, evaluated where the displacement is 0, which means it hasn't moved, that these are 0, okay, which gets rid of the linear term. We're left with that the potential of our three-dimensional function, or sorry, our 3n dimensional function is v of delta x sub 1, delta x sub 2, all the way up to delta x sub 3n is equal to 1/2 times this. Let me do it a different color because this is a scary term. I'm going to put remember we have two different types of second derivative terms. We have the cross terms and the diagonal terms. The diagonal terms are where the two coordinates in the cross terms are the same. So I is equal to j. So we're going to have a sum over I from I equals 1 to 3n, and a sum over j from I equals 1 to 3n of the derivative, of the second derivative of the potential with respect to those coordinates. Times the coordinates. Right, we get the cross terms when I is not equal to j, and we get the diagonal terms when I is equal to j. Okay, so there again, there's lots of terms. There's 3n squared of these. Right, we sum 3n and then we do 3n of those. That's 3n squared. So there are 3n terms in the potential. 3n squared terms in the potential. Right? That's really scary. Okay, so I'm just going to do a little bit of simplification now. But here's the important distinction between here. So there's a symmetry here in this symmetry. And this is a symmetry of second derivatives of multidimensional functions, but it's not too hard to see. But if we take the derivative of the potential with respect to one coordinate and then with respect to another, that's the same as doing it the other way around. Right? It doesn't matter which way I do the derivative, it's the same. Okay? So there are terms in here. Right? We have where I is equal to I and j is equal to j. That's the same value as it is if we flip the indices. If j is equal to I and I is equal to j. Okay? So we have some symmetries in here. Right? We don't have 3n squared unique terms, but we have something slightly less than that because half the term, all the cross terms are a pair of equivalent terms, equivalent numbers. They're the same. We have a factor of 2 that we have to deal with here and stuff. But let me write it like this. This is a really, really interesting thing. Right, so I'm just going to do a little bit of notation. Right, we're going to call f the number f sub ij to be this derivative. Right, this is what's called the force constant, just like before. Remember, the force constant is just the steepness, the curvature, the steepness of the slope at the minimum. Right? K. That's all it tells you, something about the potential shape at the minimum. It's the force constant. Right? So if I were to write a big matrix of all the force constants, right? So we have this big F matrix here. Right? It's going to be a big honker. All right, and I'm going to index this so that you have F00, 0, that's the first element, and then you have F10 0, all the way up along the first row. Sorry about that. To F3n, comma 0. Okay. And then you have F1, you have F01, F11, all the way up to F3n1, right? All I'm doing is I'm making an array, a matrix, or an Excel spreadsheet, if you will, of a matrix of all the force constants, right? I have the one along this is the diagonal terms here, F00, 1, 1. That's where you have x sub 0 squared in your potential. This is x sub 1 squared potential, right? And so on and so forth. Right? These are all our little force constants. There's 3n squared of these. Right? You have F22 all the way up to, at the bottom, F3n comma 3n. Right? And of course, you have all these terms that go like this. Right? I can just keep on going. Right? You have all these terms in this matrix. Right? But the important thing, and let me add one, let me just look at an example here, is that the ones that I circle here, for instance, are equal. Right? F10 is equal to F01. Right? Because they're both the second derivative of the potential with respect to the displacements of atom 0 or atom 1, whichever you want to use. Sorry, I should do these as 1, 1. I apologize. This is 1, 1, 2, 0, 2, 1. I should count from 1, not from 0. I apologize. This is 1, 2. This is 2, 2. This is 3, 3. Okay, sorry about that. Let me change that now. Again, if I counted from 0, then it would be 3n minus 1. That's just some That's just me being a programmer counting from 0. I apologize. So this is the derivative from x sub 1 and along x sub 2, like that. Right? And so it doesn't matter which way I take those derivatives, right? It doesn't matter if I take the derivative along x2 first or along x1 first, but they're symmetric. That's a rule for the second derivatives. So as I go down the diagonal, right, as I go along the diagonal, which I'll draw here, like this with my pink, right, there's going to be a term. For instance, let me just write the next one. Right, think about the terms on right off the diagonal. This is going to be f32, and then down here below it on the other side of f22 is going to be f23. Right, and of course these are equivalent with each other. Right, and again, I could do this for all of them, right? But in general, if I is not equal to j, actually that doesn't matter, because if I is equal to j, it still works. Sorry, just a sec. Right, but we have a symmetry. The symmetry is Fij is equal to Fji. Right? So the system is symmetric about the diagonal, like this. And what's even better is that all Fij, all the values are greater than 0 in real. Right? Because again, remember we're expanding around a minimum. Right? So the curvature of the potential at the minimum is always this way. So it's always going to be positive. Right? If you have a minimum, the second derivative is positive. It's convex up. Right? So all of the values in this matrix are positive, real, and it's symmetric about the diagonal. Right? And it turns out that if you have all of these things, with these combinations, I can always write I can always calculate a new set of coordinates where I get a new f prime that is entirely diagonal. f11, f22, f33, all the way down to f3n, and we have zeros everywhere else. All right, so the coordinates of this delta x sub I that satisfy this are the normal modes. Q sub I. Okay, so what we've done is we've gone from a representation of our potential where we've considered all of the atomic coordinates independently. And we get all these nasty off-diagonal elements, right? As you move one coordinate, it affects the other one, right? But because this behavior is symmetric in that if I move along one coordinate and then move along the other, it's the same as doing the opposite. And I know all of the numbers are positive and real. They have to be. They're real springs. Then I can always calculate a new version of the force constant matrix. Basically, I take this representation of our system and move it into a set of coordinates that looks like this. And these coordinates are guaranteed to be the normal modes, these collective motions that I want. They're linear combinations of all the atoms moving collectively. And they're set up so that the forces associated with them are independent. So as long if I move along one normal mode, these collective coordinates, it doesn't affect the other ones. They're all independent. Right, so these are this would imply that the Q sub i's, the normal modes, are orthogonal to each other. Right? If we wrote a vector representing these motions and we took the dot product, they'd be perpendicular to each other in this space. Right? Motion along one doesn't affect the other one. Just like motion along x doesn't affect motion along y. Right? They're independent of each other. Same idea here. Right? Except we have 3 n of them instead of 3 coordinates. We have 3 n coordinates. And they're all independent of each other and orthogonal. Okay. So let's see what these look like. All right, we are almost there. So that means now that our potential for our system, V sub q, is equal to, q sub I, sorry, is a sum for I equals 1 to 3n of 1/2 times the coordinate, the force constant, F sub I, q sub I squared. Right, this is the force constant. Right, it's our stiffness. Right, there's going to be a force constant associated with it and a reduced mass associated with it. Right, it's the same idea as our harmonic oscillator, our diatomic, but now we have 3 n of them instead of just 1. So our Hamiltonian looks like minus, right? There's 3n different coordinates, so we have I equals 1 to 3n. Minus h bar squared over 2 mu I times the second derivative along that coordinate, qi squared, plus our potential, which is 1/2 F sub I q sub I squared. Right? And so if I were just to just cheat a little bit, and if you write this like a diatomic, right, it looks like h bar squared over 2 mu d over the second derivative of the position of the bond squared plus 1/2 kx squared. Right, this is for a diatomic. Right, this is the exact same formula. We have a second derivative, right? We have a kinetic energy which is proportional to the second derivative of your coordinate plus 1/2 kx squared. Now we have these normal coordinates instead. And you have 3n of them, right? Now we have 3n, right? These are harmonic oscillators, right? We now have 3n uncoupled harmonic oscillators. And we know all the math for harmonic oscillators. They don't interact with each other, so we can solve for all of them separately. So this problem is separable. All right, and when we solve the Schrodinger equation, we get that the total wave function of the molecule is going to be the product of the wave functions for each of the coordinates each of the wave functions, right? The total wave function is a product of all of the coordinates, but they're all individual, right? So the wave function for coordinate 1, normal mode 1, doesn't have any dependence on normal mode 2. They're all separable. Right? So we can treat each one separately, and the total wave function for our molecule vibrationally is the product of all of them. And the energies, the total vibrational energy is going to be the energy along coordinate 1, along coordinate 2, plus all the way to coordinate n, 3n, where E sub I is h bar omega. All right, let me write it like this instead. H bar omega. Let me just write it like that. Omega sub I, there's one for each one, and each one has its own vibrational quantum number, p sub I. Like so. Right, so what does this say? This says that a polyatomic molecule can be represented as a sum of uncoupled, of 3n, uncoupled diatomic-like oscillators. All right. Again, I've skipped a lot of math here, but the simplification is really simple, right? We've moved our system into having these magical coordinates, which we call normal modes, where motion is independent. Right? And unfortunately, I might not have time to show them today. We might have to have Sean do your show and tell on Wednesday at the beginning of class to show you. But the idea is that we have these unique motions of the atom that are uncoupled, and they act like normal oscillators. Right? Each one has its own set of energy levels, and its own constants, and its own frequencies. And there are going to be theoretically 3n of them. What I want to do for the last 10 minutes is to identify the most trivial of these normal modes. What do they look like? And it turns out that there's 6 of them that we can immediately identify for a 3-dimensional molecule that are what I would call trivial motions, things that we don't even have to worry about. Right? This 3n is actually going to reduce to 3n minus 6. Now let me explain why. There are 6 normal modes that every 3-dimensional molecule has that aren't really vibrations. And let me explain them to you. All right, so the trivial normal modes. All right, so let's take our molecule formaldehyde. Okay, and let's say there's a harmonic, a mode, a normal mode, with the following atomic components. Okay, so I'll take my molecule. All right, and then what I'm going to do is I'm going to move all the atoms parallel to each other in some direction. All right, so this is delta x sub O, delta x sub B, delta x sub A, and delta x sub C. Okay, and all the modes, all displacements are parallel. And have identical magnitudes. Okay, so the idea is I'm going to take each of the atoms and shift them all to the right by the same amount. All right, so what happens when I do that? Well, this molecule, what happens is the molecule is initially here, right? And now all of the atoms are moving in parallel at the same magnitude. What happens? Well, the molecule just translates. All right, so if they all move in the same direction, this is just translation. Right? And the bonds, right? First of all, these are all collective motions, right? All of the atoms are moving collectively. Right? This is a normal mode. They're all moving collectively, and the center of mass of the atom isn't changing with respect to the other atoms. Right? Center of mass is going along at the same rate. Right? I'll just draw it. Right? I'm not really stretching the atoms around, and nothing's really happening. I'm just moving them. Right? So there's one. That's a normal mode. That's one of the 3 normal modes. But that's not a vibration, right? The bounds haven't moved. They've all been displaced equally. They just translated. Right? And of course, there's going to be 3 of these because there are three coordinates, right? There's x, y, and z. So there are three of the normal modes. Are just x, y, and z translation. Right? That's not vibration. That's just the atom. That's just the molecule moving in space. Right? That's not a vibration. Okay? So that's nice. We don't have to worry about those. Right? Because 3 of the modes are just translation, and if we're going to fix the molecule in place, they're not important anyway. There's another set of normal modes. These are a little harder to see. Right? What if I instead move the atoms in such a way that when I add the vectors together, right? I add the vectors together such that when you add them all together, the net vector is 0. Right? So I add tip to tail. I add all the displacement vectors together, and the net change does not change the position of the vector at all. Right? They all cancel out. But the system has, say, for instance, the atoms haven't moved, but what we've done is taken the system and flipped it upside down. Right? This is just a pi rotation. Once again, I have a collective motion of my atoms. They're all moving. My motion is a linear combination of all the motions of the atoms. But the net result is that the system hasn't changed at all. Right? I haven't displaced any of the bonds. I've just rotated the molecule. Right? Again, this is just rotation. Right? So if you have a 3-dimensional molecule, like formaldehyde, there are 3 additional normal modes, which are the rotations of molecule. Right? Those aren't vibrations, they're rotations. Okay? So 6 of these 3 normal modes are not vibrations. They're translations and rotations. So we can just get rid of them. We don't even have to think about those motions because they don't contribute at all to the vibrations of the molecule. We're just moving the molecule or rotating it. Right, so what does that mean? That means that for a 3-dimensional molecule, there are 3n minus 6 vibrational modes, or normal modes. Three and minus 6 of them. For a linear molecule, okay, something like, for instance, my favorite molecule, OCS. It's a linear molecule, carbonyl sulfide. There are only 2 axes of rotation, and so therefore you have 3n minus 5 modes. Or normal modes. Okay, so when I did all these sums of all these potential terms from 1 to 3n, right, all the coordinates, I didn't actually have to do that. I only needed to go over 3n minus 6 of them. because there are only 3 n minus 6 collective motions in formaldehyde that actually represent vibrations. So how many is that? Well, there's 4 atoms. So it's 12 minus 6. There are 6 vibrational modes of formaldehyde. 6 unique modes with 6 unique energies and 6 unique motions. What about OCS? OCS has 3 atoms, but it's linear, so there's only 3 n minus 5 modes. Right? So 3 times 3 is 5. 3 times 3 is 9 minus 5, that's 4. OCS has 4 vibrational modes. I'm not going to show you what they are yet, because I'll sit down and I'll calculate them and we'll look at them, and then I'll have Sean do an interpretive dance for you of them as well. Right? So just to close up, right? H2CO has 4 times 4 minus 6 modes, which is 6 vibrations. And OCS has 3 times 3 minus 5, 4 vibrations. Okay, so ideally, naively, what you would expect is that if you shine your light in the infrared region at formaldehyde, you would see 6 unique peaks, one at a different frequency for each of the modes. They're each unique diatomic-like harmonic oscillators with their own frequencies and their own quantum numbers. Right? So you'd see a spectrum for each one of them. Right? It turns out to be more complicated than that. You do see those 6 peaks. Theoretically, you do. Some of them you don't. We'll talk about why. But they're theoretically there. All 6 of them, they can all be accounted for. And in fact, I think I've even personally observed formaldehyde in all 6 of its vibrational modes in my own work. But there are caveats, and there are more modes than that, because what we haven't considered, for instance, is these are independent motions. Okay, so when we look at it, there's going to be one that looks like a bend and one like a stretch. These motions are uncoupled from each other. So theoretically, you can excite both of them simultaneously as well. You can have the molecule bend along one coordinate and stretch along another. They don't affect each other, so they can be independently excited. You can excite one or the other, or you can excite both. So you might expect there to only be 6 peaks in your spectrum, but you might also have to consider the fact that there are going to be combinations of them as well, the bend and the stretch together. You can combine them together like a drum, right? You know, on a drum there are certain normal modes on a drum, and if you hit the drum in a certain set of excitations, you get these resonance beats in your drum, and they can be combinations of different beats and different tones. And a molecule's vibrations work exactly the same way. There are 6 independent vibrations that act like diatomics, but now we can add them together as well. You can add one. You can have one V equals 1 in the stretch and V equals 2 in the bend, or V equals 3 in the bend and V equals 2 in the stretch. You can have any combination you want. So even though I said there's only 6 vibrations, you can have linear combinations of all of them as well. All right, so that means that the spectrum might be very complicated. All right, but at the very least, we know it at bare minimum energy, right? Nothing else, the simplest form. We haven't lost sight of diatomics. And at this basic level of theory, formaldehyde to us looks like a combination of 6 diatomic-like vibrations. All right? We'll identify those vibrations next class, and we'll have Sean help you memorize them in such a way that you'll never forget them for the rest of your life. All right, again, that might not be a good thing, by the way, but it could be traumatic. Who knows? Okay, you guys have a lovely day. I'll see some of you in an hour. Otherwise, I'll see you on Wednesday.
You're posting the midterm this upcoming Monday?
No,
Okay,
no.
sorry.
It will be I'll post it the Wednesday after we get back from spring break.
Okay, perfect.